Now, in this session, we'll continue to look at CSEC Advanced Past Paper questions. Specifically, we'll be looking at questions 4 and 5 from section 3 of paper 2 from 2023. So let's begin with this question. Now, number 4, part A. Now, number 4, part A says, function given by y equals ax squared plus bx plus c has a gradient of 9 minus a half x at a stationary value of 5. Determine the value of a, b, and c in the function. So first of all, let's write down the function that we're given. We're given the function y equals ax squared plus bx plus c. So y equals ax squared plus bx plus c. Now we're given information about the gradient of the function, 9 minus a half x, which of course really means the gradient function dy by dx, which basically suggests that at some point we have to find dy by dx. So let's just go ahead and do that for this particular function. So we'd say that dy by dx is equal to 2ax plus b. All right, so we have that. Now, what exactly do they want us to do in this particular question? It says we're supposed to determine the value of a, b, and c in the function. Now, if we go back at the first line, it says that the function has a gradient of 9 minus a half x at a stationary value of 5. So, what does this mean? It means that we also have dy by dx is equal to 9 minus a half x. Or if we want to write it in the form, we have the x term first, we can say that dy by dx is equal to minus a half x plus 9. Now, if we compare these two expressions, 2ax plus b and minus a half x plus 9, they should be equivalent, because of course they both represent the gradient function of the same particular curve. So what this therefore means is that we can actually equate these two expressions and find the unknowns. So let's do that. So we have 2ax plus b is equal to minus a half x plus 9. So here we have our equivalent expressions. And if these expressions are equivalent, it means that the like terms must have the same coefficient or they must be identical. So what does this mean? It means that, for instance, in the case of the x term or the term in x, we can say that 2ax is equal to minus a half x. This therefore means that the coefficients must be equal. So 2a is equal to negative a half, and this of course implies that a is equal to minus a quarter. All right, so we managed to find the value of a, and of course if we also compare the constants b and 9, then you should also see that the value of b is equal to 9. So by doing that and equating the gradient functions, we've managed to find the value of a and the value of b. Now what about c? Now let's look at the additional information that we're given. We're told that this function has a stationary value of 5. Now, whenever we speak about a stationary value, it typically means the y-coordinate at the stationary point. So what this basically means is that at the stationary point, the y-coordinate is equal to 5. But we need to find the x-coordinate. So remember that we have this. We have dy by dx is equal to 9 minus a half x. And if you recall that at the stationary point, dy by dx is equal to 0, right? So in order to find the x-coordinate of the stationary point, we're going to set dy by dx equal to 0 and then solve for x. So doing this, we get 9 minus a half x is equal to 0. 9 is equal to a half x, and this implies that x is equal to 18, right? And what this therefore means is that the x-coordinate of the stationary point is 18, and since we're told that the stationary value is 5, then this further implies that the stationary point is the point 18, 5. So we've managed to find the coordinates of the stationary point, but what else do we need to find? We need to find the value of c. And of course, if we go back to the original equation, we see that y is equal to ax squared plus bx plus c, right? That will just make some space here. So we have y is equal to ax squared plus bx plus c, but we've already found the value of a and we've already found the value of b. So what this therefore means is that y equals, so a was equal to what? A is equal to a quarter, that is minus a quarter x squared plus 9x plus c. And since, of course, we found the coordinates of the stationary point, which is 18, 5, then what this basically means is that y is equal to 5 when x is equal to 18. And so we'll substitute these values into our equation and solve for our unknown c, right? So let's do this. So we have 5 is equal to minus a quarter times 18 squared plus 9 times 18 plus c, right? So let's continue. So we have 5 is equal to minus a quarter. We go to our calculators. What is 18 squared? So 18 squared, that is 324. So minus a quarter times 324 plus 9 times 18. 9 times 9, that is 81. 81 times 2, that is 162. So this is 162. So therefore we have 5 equals, now 324 divided by 4, that is 81. So 5, oh, I forgot the c, plus c. So we have 5 is equal to minus 81 plus 162 plus c. 5 is equal to 81 plus c, and therefore c is equal to minus 76. So we've managed to find the value of c, our last unknown, and essentially we can therefore write down the equation of the function, which of course we're not required to do so, but having found the values of a, b, and c, we can simply say that y is equal to minus a quarter x squared plus 9x minus 76. And that, of course, would be the function. So that was part one of the question. Now let's move on to part two, right? Now, part two says, determine the nature of the stationary point, right? So how do we go about determining the nature of the stationary point? Since we already have the first derivative, what we will do is we'll find the second derivative and then evaluate the second derivative at the start at the stationary point, okay? So let's go ahead and do this. So we know that dy by dx is equal to minus a half x plus 9. That was it? Yes. Now 9 minus a half x. Same thing. So dy by dx is equal to 9 minus a half x. And if we differentiate a second time to find the second derivative, we get that d2y by dx squared is equal to 0 minus a half times 1 is equal to negative a half. Now, what does this mean? The second derivative has no exterminate. Now, usually, whenever we get a question like this to determine the nature of the stationary point, when we differentiate the second time, the second derivative is also a function of x, and then we can actually substitute the x-coordinate of the stationary point into the second derivative. But in this particular case, the second derivative is just a pure number. So d2y by dx squared is equal to minus a half. And therefore, what this tells us is that the stationary point is indeed a maximum because the second derivative is always negative. So because the second derivative is always negative, then it means that the stationary point, which of course is a point 18, 5, is a maximum point. And that is the nature of the stationary point. All right. So that was part 2 of part A. Let's move on to the next part of the question, which has a graph. All right. So that part is complete. Now let's look at part B. Now part B says a drone tracks the movement of an object in motion on the ground. The following movements are recorded. First one, it moves at a constant velocity of 4 meters per second for 5 seconds. Its velocity increases uniformly for 3 seconds to 10 meters per second. That's the second stage. The third stage, it moves at that velocity for 7 seconds. And by that velocity, they're talking about the 10 meters per second. All right, so we have to read the question carefully. And lastly, it slows uniformly until it comes to rest after 4 seconds. Now they want us to sketch a graph of the movement of the object. So clearly what we have here is a graph which shows velocity in meters per second on the y-axis and time in seconds on the horizontal axis. And we need to be able to sketch a graph of this body's motion. Now, we need to figure out what the maximum velocity is so we can actually choose our scale appropriately. And we need to also figure out how long the motion lasts so we can actually choose a scale for our time axis. So we see that the maximum velocity is 10 meters per second. And so if we choose a scale, I will try to choose a decent scale. So we're going to take this as 0, 0, let's see, this would be 2, 4, 6, 8, 10. That could work. So 0, 2, 4, 6, 8, 10. So let's work with that here. So this would be 2, 4, 6, 8, 10. All right. Now for the time axis, let's see the times that we're talking about here. So for 5 seconds, then another 3 seconds, that's a total of 8 seconds. Then 7, that's 15, and 4, 19 seconds in total, right? So let's see how we can do this to take up as much of the graph paper as possible. Obviously, if you use 1-to-1 is out of the question. But this will be 2, 4, 6, 8, 10, 12, 14. Now that won't reach 19. So how about, let me see now, this will be 5, 5, 10, 15, 20. Yeah, that could work. That could work. Let's use that particular scale. So let this be 5 seconds, 10 seconds, sorry, 15. So 15 seconds right here and 20. All right. All right. So let's see what's going to happen on this graph now. What are we told? So let me just clear the screen a little bit. The first piece of information is that we're given that the body moves at a constant velocity of 4 meters per second for 5 seconds. Now we need to show this on the graph, and so we're going to locate 4 meters per second on the vertical axis, and we're going to draw a horizontal line which lasts for 5 seconds. All right, so that's that stage right there. Good. Now for the next stage we're told the velocity increases uniformly for 3 seconds to 10 meters per second. So currently we are at 5 seconds, right? 5 seconds. And so if we in retrospect, this is probably not the best scale that we could have chosen, but let's work with it. At the end, we could probably choose a slightly different scale so that the graph actually takes up as much of the graph paper as possible. All right. So if that is, yeah, let's finish off the question with this particular scale, right? So that's up to 5 seconds. Now it says the velocity increases uniformly for 3 seconds to 10 meters per second. So we're going to go now from this stage right here to 10 meters per second in a time of further 3 seconds. So we're going to go up to 10. Now this is supposed to take 3 seconds, right? So this would be 7.5 and this would be 8 right here, right? So this would be 8 seconds right here because essentially 2 small squares will be equivalent to 1 second. All right, so that stops right there. Good, that's the second stage. The third stage says that it moves at that velocity for 7 seconds. So 5 plus 3 gives us 8, And for further 7 seconds, you're going to stop at 15. So we're going to draw a horizontal line from 7 to 15. So it's going to stop right there, right? And then lastly, what we're told is that it slows uniformly until it comes to rest after 4 seconds. So currently, it has been moving for 15 seconds, and it's going to come to rest in a further 4 seconds, which means that the total time of the motion will, of course, be 19 seconds. And so we'll continue from there. We draw a straight line sloping downwards, stopped at 19, which would be right here. Good. Right. And essentially, that is our graph of motion, right? So basically it shows a particular scale on the x-axis. I mean, the graph did not take up the entire graph paper, but the most important thing is that the information that we actually showed is what we needed to show, all right? So let's continue. Now, the next part of the question says, well, sketch a graph of the movement of the object, and we've done that. So 3 marks. So we showed the first segment where the body moved at a constant velocity of 4 meters per second for 5 seconds. Then secondly, its velocity increased uniformly for 3 seconds up to 10 meters per second. So that was between 5 and 8 seconds, right? Next, its velocity was maintained for 7 seconds, so that was at 10 meters per second, which meant it went up to a time of 15 seconds. And then lastly, its velocity decreased uniformly to rest in a further 4 seconds, right? So let's skip ahead to the next part of the question and see what they actually ask us to find. Now, they want us to calculate the distance traveled by the object in the second part of the journey. Now, the second part of the journey, of course, we're talking about this stage where the velocity increases uniformly for 3 seconds at 10 meters per second. Now, if we have a graph of velocity against time, how do we determine distance traveled? Distance traveled is obtained by finding the area under the graph, okay? Let's just try to identify the segment that we're dealing with. So let me use some black lines. So the segment for 5 seconds we're talking about here. All right, so between 5 and 8, which is right here. Right? So we're talking about that little segment there, right? Between those two vertical black lines. And so what we need to do is to find the area of this segment, right? Now, what type of shape is this? Between 5 and 8 seconds, essentially we have a trapezium. But of course, we can split the trapezium into a rectangle and of course a triangle. Let's do that. So let's draw a horizontal line right here to split the trapezium into a triangle and a rectangle, right? So in terms of the rectangle, let me just shade it to show you exactly what we're speaking about. We're talking about this region right here as our rectangle. And of course, for the triangle, we're talking about this region right here, right? So let's go ahead and find the distance traveled between 5 and 8 seconds. So the distance traveled is equal to the area under the graph, right? And again, because I split up the shape into a triangle and a rectangle, let's focus on the triangular section first. Now, the triangular section, it is a base between 5 and 8 seconds, so a base of 3. It is a height of between 4 and 10 meters per second, so a height of 6. So this is base times perpendicular height divided by 2, okay? Now for the rectangular portion, it has a base of between 5 and 8 seconds, that's a base of 3, and a perpendicular height of between 0 and 4, so this is plus 3 times 4. So this gives us 3 times 6, 18, 18 divided by 2, this is 9 meters, plus 3 times 4, 12 meters, which gives a total distance of 21 meters. Now, many students, because they're used to calculating area in meters squared, once they hear about calculating area, they will proceed to write down the unit as meter squared. But you have to remember that this type of situation is where you're finding the area below a speed time graph or a velocity time graph. And the area below a speed time graph a velocity time graph gives us a distance traveled in meters, right? So it gives us a distance traveled in meters. And so therefore, we're not going to put meters squared for the area, but meters, because that is what the area under the velocity time graph gives us, okay? Now, let's go ahead and see what else the question asks of us. So we managed to find the distance traveled by the object in the second part of the journey. Now, they also want us to determine the object's acceleration in the final part of the journey. Now, let's look at the graph and identify the final part of the journey. The final part of the journey, of course, is this part right here. Where's my cursor? This part, which says it slows uniformly until it comes to rest after 4 seconds. So that stage is characterized by this straight line segment. Let me just put some letters. Let me put some letters on the graph. So let's call this A, B, C, D. So this final stage that we're talking about is CD. And they want us to find the acceleration of that final stage. Now, how do we find acceleration from a velocity time graph? We find the gradient of the graph, or the gradient of a particular section of the graph. Now, what are the coordinates of this point at C? This point will have time value of 15 seconds and a velocity value of 10 meters per second. So essentially, its coordinates are 15, 10. And this point down here, D, would be at time t equals 19 seconds and velocity 0, right? So for the final stage CD, the acceleration A rather, is equal to the gradient of the segment CD. And we know the formula is y2 minus y1 over x2 minus x1, or since it's a velocity time graph, we can say that is going to be equal to the change in velocity, delta v, divided by the time taken, t, right? And therefore, the acceleration A is equal to 0 minus 10 divided by 19 minus 15. And so this gives us minus 10. Units, of course, are meter per second. And, of course, this would be 19 minus 15. That is 4 seconds. So divided by 4 seconds. And so this gives us negative 2.5 meters per second squared. And so the acceleration for this segment is, of course, minus 2.5 meters per second squared. The body is decelerating uniformly, and eventually it comes to rest in a time of 4 seconds. All right? Is there anything else for this question? No, but I did mention that the scale I initially chose was not the best, given the fact that our graph did not take up, well, barely took up half the graph paper. But in a question like this, they're probably not really marking that much for scale, but the accuracy of your sketch. But anyways, let me just redraw the graph using a slightly bigger scale, so it takes up a little bit more space on the entire graph. All right, so I'm going to adjust the scale for the time axis, right? Let me see what other scale I could probably use here, just to make sure it takes up a little bit more space. So let me see what I could use here. If I let this be, say, 4, it's a good scale. 4, 8, 12, 16, 20. Doesn't make much big of a difference, to be honest. And it's just going to be a little bit more problematic in actually finding the values that we need to find. So, yeah, I think we could probably leave it. We could probably leave it. Let me see how another scale would be. Let me see. 3, 6. In retrospect, let's just stick to the one that we actually chose, right? Because using this particular scale makes it a little bit more difficult to locate a value like, say, 5. This would be 6 right here. This would be 6. And then 5 would be midway between 4 and 6. But anyways, let me just go ahead and do it. So this would be 4. So using this particular scale, of course, we know that between 4 and 8 would be 6. So this essentially would be 2, 4, 6, 8, 10, 12, 14, 16, 18, and so on, right? 22, 24. Anyways, so yes. So 4 moves at constant velocity for 5 seconds. We draw a horizontal line at 4. Come to the midpoint or midway between 4 and 6, right? So it's going to stop right about there, all right? And then it's going to move from there to 10 meters per second in a further 3 seconds. So that's going to go up until about 8. So we're going to go up to 10 and it's going to stop at, say, 8. So 3 seconds, right? Up to 8 seconds. Good. And then from there now, it's going to move at that velocity for 7 seconds. So over onto 15. So 15 will be midway between 14 and 16. So about there, right there. And then lastly, it's going to move from a velocity of 10 meters per second to rest in a further time of 4 seconds. So it's going to come to rest at 19 seconds, right? So I'm going to draw that down here. 19 is right there, right? Right, so that's basically what the graph looks like. I mean, the shape remains obviously the same, but just with a slightly bigger scale. But ultimately, we'll get the same result if we were to actually redo the calculations. All right, so let's move on from this question. All right, so that was question 4. Now, let's look at question 5. Now, question 5 says, consider a toy truck moving along a miniaturized racing course with an acceleration of a of t equals 9t squared plus 2t minus 1, where t is the time in seconds. Assume that the speed of the truck, or the toy truck rather, is measured in centimeters per second. It says, outline how an equation for the speed of the truck would be found using the given equation for the acceleration. Now, it did not ask us to find the equation for the speed. It asked us to outline. In other words, we're supposed to use or to give a worded statement. So what you would say is that you integrate the acceleration with respect to time, or integrate a of t with respect to time. And let me see what else they gave us. So yes, that's essentially what you need to do, all they gave us is the acceleration formula. They didn't give us any initial conditions as yet. So you basically integrate a of t with respect to time, because what do we know? We know that acceleration a is equal to dv by dt. So when you have velocity as a function of time, it means that you will differentiate with respect to time to get acceleration. And therefore, what this means is that because integration is essentially reversal of differentiation, would say that the velocity v is equal to the integral of a dt, right? So v is equal to the integral of a dt. And of course, if we responded accordingly, we should get the 1 mark, all right? So in part 2 now, they want us to find the speed of the truck at t equals 10 seconds, right? So once again, we have the acceleration as a function of t. So say a of t is equal to 9t squared plus 2t minus 1, right? So consider a toy truck moving along a miniaturized racing course with an acceleration of a of t equals 9t squared plus 2t minus 1, where t is the time in seconds. Assume that the speed of the toy truck is measured in centimeters per second. Now, they want us to find the speed of the truck at t equals 10 seconds. Now, first of all, we're going to say that v is equal to the integral of a dt, which of course is equal to the integral of 9t squared plus 2t minus 1, and we're going to integrate that with respect to time. And therefore v is equal to, so integral of 9t squared, 9 is our multiplying constant, so we keep it. So this becomes 9t cubed all over 3. Then we have plus 2t squared over 2. Remember, when integrating, we increase the power by 1, divided by the new power. So 2t squared over 2, and then we have minus t, plus, of course, our integration constant c. Now you have to remember, Once you're executing indefinite integrals, you should introduce your integration constant. And we can then proceed to go and simplify this. So what we have is this. We have v is equal to 9t cubed over 3 plus 2t squared over 2 minus t plus c. So say that v is equal to 3t cubed plus t squared minus t plus c. Now, what about our integration constant c? Now, in reality, we were not given any information to determine the value of c. So what we could probably do is assume, right? This is an assumption. Assume that at t equals 0, v equals 0. In other words, then, we assume the body was initially at rest, right? So at time t equals 0, v is equal to 0. And if we make the assumption, we could do the substitution, and so you get that 0 equals 0 plus 0 minus 0 plus c, which therefore means that our integration constant c would be equal to 0. And therefore, our equation for the velocity is v equals 3t cubed plus t squared minus t. Okay, so this obviously is a function of time. And if we want to find the speed of the truck at 10 seconds, we can say that v of 10 is equal to 3 times 10 cubed plus 10 squared minus 10. 10 cubed is equal to 1,000. 1,000 times 3, that's 3,000 plus 100 minus 10. And this gives us 3,090 centimeters per second, right? So our assumption that at t equals 0, v equals 0 allowed us to find a value for our integration constant c. And having done that, we're able to find the velocity in centimeters per second, or the speed in centimeters per second, after 10 seconds, which worked out to be 3,090 centimeters per second, right? So that is part 2 of the question. Now, part 3 says, find the distance covered by the truck between 5 and t seconds. Express your answer to the nearest whole number. Now, how do we get distance traveled given velocity, what is a function of time? Now, if you look back at the previous part of the question, we saw that acceleration A is the derivative of velocity with respect to time. And so therefore, if we have velocity, which is a function of time, and we want to find the acceleration, we would differentiate. If we are given the reverse, if we have the acceleration, which is a function of time, and we want to find the velocity, we have to integrate acceleration with respect to time to give the velocity. In other words, A is equal to dv by dt, which therefore implies that v is equal to the integral of a dt. Now, a similar relationship exists between velocity and distance or displacement. And so we can therefore say that v is equal to dx by dt, which therefore implies that x is equal to the integral of v dt. So if we have velocity or speed, which is a function of time, and we want to find the expression for the distance, we of course would integrate, right? Now, in this particular case, we're told to find the distance traveled between 5 and 10 seconds. When you see information like that, what it means is that what you're expected to do is evaluate a definite integral. And so basically, you're expected to integrate the expression for the velocity between the limits of 5 and 10. And it therefore becomes a definite integral, and we would not have to worry about an integration constant, right? So this is the final version of the velocity that we're talking about. Let me highlight it, this one right here. And that is what we're going to integrate in order to find the expression for the distance traveled. So let's do it right down here. So we can say that the displacement x is equal to the integral of v dt. In this case, it's a definite integral. So we say x is equal to the integral of 3t cubed plus t squared minus t, that is between the limits of 10 and 5 seconds. So t equals 10, t equals 5. And of course, you have to put our dt, all right? So let's proceed to integrating this. So we say that x equals, so 3t cubed, so that's going to give us 3t to the power of 4 divided by 4. Then we have plus t cubed over 3, then minus t squared over 2. And this is to be evaluated between 10 and 5, right? So we're going to get some large numbers. So let's go ahead and do this. So we have x equals, so if we go to our calculators, so we have 3t to the 4th, so that's 10 to the power of 4, right? So 10 to the power of 4. And then, of course, that's 10,000 times 3 divided by 4. That's 7,500 plus 10 cubed over 3. 10 cubed, that's 1,000 divided by 3. That's approximately 333. How many decimal places they said? Or is it to the nearest whole number? But let's just work with 2 decimal places for now. Then we have minus t squared over 2. That's 100 divided by 2, 50. So this is the first bracket where t is equal to 10. And from that, we have to subtract the second where t is equal to 5. So we say 5 to the 4th, that should be 5 cubed is 125 times 5, that's 625. 625 times 3, that's 1875. 1875 divided by 4, that's 468.75. 468.75. Then we have plus t cubed, that's 125. 125 divided by 3, that's 41.67. So 41.67. Then we have minus 25 divided by 2, that is 12.5. And so we'll evaluate this. So in the first bracket, we basically have x equals 7,500 plus 383.33. So that's 7,883.33 minus, this one I have to go to my calculator, 468.75 plus 41.67 minus 12.5. And that is 497.92. So 497.92, not 29, 497.92. And so this gives me, so let me say subtract 7883.33, which is 7385.41. 7385.41 is approximately equal to 7,385, and this of course would be centimeters to the nearest whole number, right? So since of course our speed was given in centimeters per second and our time is in seconds, then naturally our distance traveled will be in centimeters, okay? All right, so that should be your answer there, barring any mathematical errors. So that should be your answer, but of course the principle would remain the same. All right, so that was part 3 of A, and last part of part A. Now let's look at part B of the same question. Let us make some space here. All right, so part B says we're supposed to integrate or find the integral of 2x plus 3 all squared. So this, of course, is the integral of 2x plus 3 all squared. Now, we must remember that this is basically of the form integral of ax plus b to the power of n dx, which gives us ax plus b to the n plus 1 divided by a times n plus 1 plus our integration constant c, right? So essentially, what this means is that our a is equal to 2 and or n is equal to 2. I mean, b is not really of that much significance. And so we can therefore say that the integral of 2x plus 3 squared dx is equal to 2x plus 3 cubed over 2 times 3 plus our integration constant c. So this gives us 2x plus 3 cubed over 6 plus our integration constant c. All right? So that was part 1 of B. Now the next part deals with integration of a composite trig function. So the integral of 5 cos 2x dx. So we know that as a basic integral of cosine, integral of cos x dx is equal to sine x plus c. We know that much. However, this is not just a standard or a single cosine cos x. It's a composite function. And we basically do this. So the integral of 5 cos 2x dx. Now, the 5 is a multiplying constant, so we'll actually keep our 5. So this would actually give us 5. And typically, when we integrate cosine, we get sine. So we first write down 5 sine 2x. But because this is a composite function and we're integrating 5 cos 2x, we're going to divide by the 2. So this is going to be 5 sine 2x over 2, and we have plus our integration constant c. So when we differentiate a composite trig function, we normally multiply by the derivative or multiply by that number. But in this case, we're integrating rather, and we divide by 2. So the integral of 5 cos 2x is 5 sine 2x over 2 plus the integration constant c. All right, so let's move on to part C, last part of this question. Now, part C says if dy by dx equals 6x minus 10 and y equals 12 when x equals 0, find the equation for y in terms of x. This is basically what we call, a differential equation, to be honest. So what we have is this. Dy by dx is equal to 6x minus 10. So here we have basically the gradient function. And in order to get y in terms of x, we need to integrate both sides with respect to x. Now, what we will do is we'll say that integral of dy by dx with respect to x is equal to the integral of 6x minus 10 dx, right? Now, many persons, when approaching such a problem, they would say, well, you separate the variables and you bring the dx over to the next side to keep the dy by itself. But sometimes that may give the impression that dy by dx is like a fraction, like a half, and you can basically separate the numerators from the denominator and things like that. So I just prefer to just integrate both sides. And then, of course, we know that the integral of the derivative of a function is just the function, right? So remember that integration is essentially the exact reversal of differentiation for the most part. So when we speak about dy by dx, dy by dx is essentially the same thing as d by dx of y. In other words, the derivative of y with respect to x. And if we were to integrate that, we simply say that the integral of d by dx of y with respect to x is simply equal to 1. Okay? So if you differentiate a particular function and you integrate the result, you're going to get back the original function, because integration is essentially the exact reversal of differentiation at its simplest, right? So at its simplest, that's exactly what it is. And so we'll continue with this. So we'll say that the integral of d by dx of y with respect to x is equal to the integral of 6x minus 10 with respect to x. And so this means that what we have is y is equal to 6x squared divided by 2 minus 10x plus our integration constant c. Now we must remember that whenever we execute an indefinite integral, we must introduce our integration constant, right? And in many cases, we'll be given sufficient information to find the value of that constant, right? So let's continue. We say that y is equal to 3x squared minus 10x plus c. And what information are we given? We're given that y equals 12 when x equals 0. And so if we substitute that, we get that. So y equals 12 when x equals 0. And therefore, this means that 12 is equal to 0 minus 0 plus c. And therefore, c is equal to 12. And having found the value of c, we can therefore write down our equation. And our equation is y equals 3x squared minus 10x plus 12. And that right there is our equation. Right? So that is the end of this question and the end of this section from June 2023 AdMaths paper 2.